Thank you very much. Good morning, everybody. Thanks for abandoning breakfast for this first talk of the day, and thank you for the introduction. So thanks to the organizers for inviting me, and a very happy birthday to Liz. Very glad to be able to speak about conservation laws and computation at this particular session especially. Okay, so we've heard a few talks about finite difference methods in conservation laws. I'm going to take a slightly different approach and talk about a different class of numerical methods, finite element methods and conservation laws. So first of all, let me just briefly say what kind of conservation laws I'm talking about and what might be one of the challenges for using finite element methods to talk about these. So first of all, there are a lot of conservation laws that are local in space and or in time, and we can usually express them in sort of a differential expression in some sort of infinitesimal way, which is maybe useful for doing calculus but not so useful for computation, and we can usually integrate it over something and get a finite expression of the conservation law. So for example, if we had some quantity rho that's conserved in time, right, to say that it's conserved in time is that its time derivative, which I'm writing with a dot, is 0 for all t in some time interval, right? And of course, if we integrate it over a particular time interval, tk to tk plus 1, rho being conserved just says that the value of rho at step k plus 1 is the same as the value of rho at step k. If we have a conservation law in space, like maybe for an elliptic PDE or something like that, it would be saying that the divergence of something, which I'm calling J, so I'm thinking of rho as being like a charge, J as being like a current, the divergence is 0 for every point in the domain of our PDE. And an integral version of that is, of course, if we take some subdomain K that's compactly contained in our original domain, we can integrate and apply the divergence theorem just to say the flux of J through the boundary of that region is 0. And right, we can combine these and get some sort of space-time conservation laws. So if we've got a charge rho and current J, right, the differential expression is that rho dot plus div J equals 0. And if we integrate just in space, we get something like this, which basically says that the change in charge within K is balanced by the amount of current that flows in or out through the boundary of K. Right, and then we can also do the thing where we integrate over a time interval and get an expression that's discrete in time as well. Okay, so a lot of previous approaches to discretizing PDEs in such a way that satisfy conservation laws is focused on finite difference or finite volume methods. So for example, for a finite volume method, you can very easily take a look at something like this. Right, and the variables in your finite volume method would be precisely, say, the charge within each cell K at different steps in time, and then in between steps you would have some sort of flux through the boundary. Right, so these things would literally be your variables. Right, and it's the way one typically does this for a finite difference or finite volume method is you sort of look at this local stencil that basically describes how you discretize the derivatives, how values at certain points are related to the neighboring points. And you maybe write this up and say, you come up with some discrete analog of, all right, what's a discrete divergence mean for this particular kind of method? And you come up with a way of seeing whether in sort of this analogous discrete sense, you might have something like this conservation law holding. Finite element methods are wonderful from the perspective of analysis because you basically have all the, right, rather than just having values at a number of points, right, you essentially have interpolants. You're basically working in some function space, typically, some LP space or Sobolev space. and you have all of the power of analysis at your disposal to do stability and convergence analysis, and you have very high order methods. So analysts and numerical analysts and engineers love these. But what's the idea is typically you have some global space of functions on U, just some enormous infinite dimensional vector space. You then triangulate your domain, you decompose it into usually simplices, and then you restrict some variational problem corresponding to your PDE, some infinite dimensional variational problem, to a finite dimensional subspace of piecewise polynomials on your triangulation. So that basically you have it now gone from an infinite dimensional variational problem to a finite dimensional one. And the problem is that, if I just take a vector in some big infinite dimensional vector space, it's a little bit hard to talk about localizing this decay. So you can't just, so if you look at a finite difference method, the stencil is very easy to understand locally. For a finite element method, you can't do all the things that we're used to doing with PDEs. You can't just say, all right, I'm going to take this solution, and if I restrict it, and I take the same boundary values, and then solve again, I'm not necessarily going to get the same thing, So localizing finite element methods is a little bit tricky. You also have to be careful with when traces are defined, So if I have some function that lives in L2, maybe it's say piecewise constant on elements, I obviously can't talk about a pointwise value of some function that's in L2. So I would say that really the difference is between finite difference and finite elements, if I had to sort of oversimplify, is that for finite differences in finite volumes, it's very clear sort of what local pointwise values are. You can localize very easily, and you have to be a little bit clever about how you define your differential operators, You have to come up with discrete analogs of everything. And I think for finite element methods, you don't have to be really clever about the differential operators. You don't have to say what is a discrete divergence. It's just divergence, Everything is just your original problem restricted to this finite dimensional space. But you have to be clever about the opposite things, which is how to talk about things locally. And I think this challenge is one of the reasons why people looking at structure-preserving methods, conservation laws, haven't looked as much at finite element methods. However, there's a class of finite element methods called hybrid finite element methods that work as follows. The basic idea is that you, first of all, you relax your global function spaces on U so that you can have things being completely discontinuous between different simplices, So you don't have any continuity conditions at all enforced on the functions in one simplex and the functions at its neighboring simplices. But you then introduce new variables on the boundaries that are going to end up acting like approximate traces, and these enforce certain continuity conditions. So this basically decomposes into a collection of local solvers, one for each simplex, and they're coupled together through these new variables, these approximate traces. You can also sometimes think of them as Lagrange multipliers. So the general idea that I've been working on, and I'm going to talk about sort of this general idea and two particular instances of this idea, is the following, is basically to take PDEs that have some sort of conservation law or local symmetries and come up with hybrid methods and look at whether the conservation laws are satisfied in the sense of these approximate traces, in the sense of these new variables that live on the boundary, and then you can really look at whether things like this are satisfied. So that's the general idea that I'm going to be telling you about today. So first, let me just give a quick example of how the finite element method and how a hybrid finite element method look for sort of a simple problem. So let's look at Poisson's equation, which just in strong form we would write as minus Laplace u equals f. I'm just putting Dirichlet conditions on the boundary. So if I wanted to write this problem in variational form as I would for a traditional finite element method, So I'm going to take U, I'm going to look in this space that I write H1 U with a little circle over it, and that just means the Sobolev space H1. This is functions U that are in L2 whose gradient is also in L2 in the sense of distributions, and this little circle just means the vanishing boundary trace. Right, and the trace theorem tell me I can make sense of that. All right, so I can define the following action integral, which is just half grad U norm squared minus f times u, right? So this is sort of a Lagrangian. I'm integrating it over u, and this is my action integral, and I want to extremize that. Right, so if I take a variation of this in the direction of some other function in the Sobolev space, some test function v, right, I get equivalently that to be a critical point of this, it has to satisfy integral grad u dot grad v equals fv for all v. Right? And in terms of things not pointwise being well defined, right, observe that if I wanted to look at the flux of u through the boundary of, say, some subdomain, right, grad u, right, if u is in H1, grad u is in L2, and that means I can't really make sense of a trace of something that's in L2. Right? So in this formulation, talking about the flux of u, right, and therefore really talking about conservation laws of any sort is kind of challenging. On the other hand, let me define this relaxed version of the Sobolev space, which I'm going to write, so I've got my triangulation TH. I'm going to define H1 of TH just to mean that U is not necessarily in H1 on the entire domain, but it's just in H1 on each individual simplex, right? So that it can be discontinuous between simplices, but within each simplex, it's going to be H1. Right, obviously I can't just use the same action because then these regions are completely disconnected from one another. So I'm going to introduce these new variables, which I'm going to call sigma hat, often in sort of the hybrid and also discontinuous Galerkin literature. You'll see hats on approximate traces and fluxes that lives on the boundary, which I'm writing as EH here. E stands for edges. People are normally thinking about 2D triangulations. Right, so I take the same Lagrangian, but now I add a penalty, sort of a penalty term. Right, so if I sum over all the k's of sigma hat u on the boundary, right, sigma hat is going to be multiplied for each edge by the jump in u across that edge. Right, and I can think of sigma hat as acting like a Lagrange multiplier that tries to make u continuous across the interface between neighboring simplices. Right, so it's a sort of Lagrange multiplier, and when I take variations along v, right, I get this expression, so I get an additional integral over the boundary of sigma hat times v, and then, right, if I take variations of sigma hat itself, I also get another equation, right, varying the Lagrange multiplier, which tells me that actually, in fact, u does have to be continuous across the boundary. And the interesting thing is if you look at this expression, right, you can see that in sort of a trace sense, sigma hat is in fact the flux of u through the boundary. So by introducing this new variable, it sort of stands in for this thing that we couldn't make sense of in the original formulation. So the idea of a classical finite element method would be, I would take this problem and restrict u and v to live in my space of piecewise polynomials. A hybrid finite element method would be, I now instead take this formulation, and in addition to restricting my u's to come from the space of piecewise polynomials on the simplices, I also restrict, right, these new variables, sigma hats, to be in some piecewise polynomials that live on the boundaries. All right, so that's sort of the idea of hybrid finite element methods. Right, and if there's one picture I would like you to hold in your head throughout this talk, it's sort of the following cartoon of classical finite element methods versus hybrid finite element methods. So here, this is my cartoon of a classical finite element method where I've got my u's defined on the interior of each triangle, right? And on the boundaries and interfaces between triangles, right, I've got these things that stand for the boundary values of u. Basically, I enforce that these two triangles share the same values on these boundaries, right? And also these are the boundary values. Whereas with a hybrid finite element method, here I introduce these new variables that I've drawn in red, sigma. So now each triangle sort of has its own boundary values, which I've drawn in dark blue, right? But they're not shared, right? They don't talk to one another, right? Instead, these triangles only talk to one another through the red stuff, right? So the thing that I've drawn in red, right, ends up being right, containing all the global information about how the different regions are coupled to one another. And ultimately that means, right, it contains, right, sort of the information about any sort of conservative or dissipative behavior of the method. So that's sort of the cartoon picture right there. Okay, so that's sort of the introduction. So I'm going to talk about two different implementations or applications of this idea. The first has to do with methods that preserve a multisymplectic conservation law for Hamiltonian PDEs. And this is joint work with Robert McLachlan, a paper that we posted to the archive last year that you can find. And HDG stands for hybridizable discontinuous Galerkin, which is something that I will explain. It's a particular class of hybrid methods that happens to sort of unify with discontinuous Galerkin methods. And I will also discuss some much newer work that we hope to have a paper up in the next few months. We're in the process of writing it up with Yakov Berchenko-Kogan. If the name Kogan sounds familiar to you, there's a reason for that. It's actually Irina Kogan's son, who's a postdoc at WashU working with me. So I'm going to talk about hybrid methods for gauge theory and the question of charge conservation. Okay, so let's start with the first one, which is multisymplectic HDG methods. So these are going to be, two topics are going to be slightly independent to one another. So here's sort of a motivating example for what the multisymplectic conservation law looks like and what it means for a particular Hamiltonian PDE. And here I'm mostly going to be talking about right, elliptic PDEs. You could also, if you have a hyperbolic PDE, you could semi-discretize the elliptic part and then use a geometric integrator for the time part. But anyway, for the most part, I'm thinking about spatial discretization. So consider the semi-linear Poisson equation. So here I have minus Laplace u equals f, but f may depend both on x and on u itself. All right, so let's suppose that v and v prime are perturbations or variations of u. Right, so I've got a solution u that satisfies this. I linearize, and I have two solutions to this linearized PDE. Right, so now this just looks like this is a nonlinear or semi-linear equation. This is basically just like a Poisson equation. Right? And if I do a little bit of vector calculus using Green's identity, I see that if I look at these two solutions, v and v prime, if I take the divergence of v grad v prime, that equals this expression by Green's identity, and this is symmetric in v and v prime, so it's actually also the same as div v prime grad v. Right, so I could switch this expression is symmetric in v and v prime. If I integrate over a region subdomain K, right, I get the following sort of integral expression of this. And what does this say? This tells me that the Dirichlet-Neumann operator, right, which takes the boundary values to the boundary flux, is actually a symmetric operator on the boundary. Right, so that's precisely what this means. And this is actually an important instance of a general phenomenon, right? Basically telling you, right? So this tells me, right, if I perturb the Dirichlet values of a solution, right? It tells me what happens to how it responds by changing the Neumann values and vice versa, right? And there are a lot of these Green's reciprocity in electromagnetics, which is applied all over the place, electrical impedance tomography, for example. There's Betty reciprocity and elasticity. So these sort of symmetries between sort of perturbations of the boundary values to a system and the response show up a lot. Okay, so what exactly does it mean? Where does this property come from? And what kind of finite element methods might preserve something like this property? Again, it should be clear already why we might want to use hybrid methods, because right, in order to talk both about sort of boundary values and boundary fluxes, this is something that really I can usually make sense of only one or the other in the classical finite element formalism. All right, so here's the general situation of which that was a specific instance. So I'm going to talk about Hamiltonian PDEs in a canonical sense. So I'm not going to be working in jet bundles or anything fancy like that. I assume that I've got a domain U in Rm, Euclidean space, right? And my phase space here, I'm going to look at U cross Rn cross Rmn. So I have n variables, sort of ui, and if you're used to thinking of Hamiltonian mechanics, my u's are like q and my sigmas are like p, right? Except right, if I'm only in time, m equals 1, then I just have qi and pi, right? Because I've got my conjugate momenta to the time derivatives. But here I have m times n of these, because I sort of have conjugate momenta for the partial derivatives of ui in each of the mu directions from 1 to m. All right? So if I'm given a Hamiltonian of x, u, and sigma, these are the de Donder-Weil equations, which basically say that grad u is partial h partial sigma, and minus divergence sigma is partial h partial u. Here I'm using the Einstein index convention, so right when you see this mu twice, it means that there's a sum over mu. Right, so this is the generalization of the canonical form of Hamilton's equations in Q and P. And I can define the following canonical two forms. Right, so this is part of why it's sometimes called multisymplectic or polysymplectic. Instead of just a single two form, dqi wedge dpi, I have this collection of them, one for each space direction. Right, so it's dui wedge d sigma I mu for each mu from 1 to m. And solutions to these equations satisfy this conservation law, which is basically the divergence, right, of, I can think of this as a vector valued two form also. I can think of the divergence of that vector valued two form as 0. Which I can also then apply the divergence theorem and write this integral expression of this. And here dm minus 1 x mu is just is basically the contraction of partial x mu with the volume form, so it tells me how to take surface area. All right. So what does this say? Well, what this conservation law actually says is that if v tau and v prime tau prime are perturbations of a solution u sigma, right, then I have this basically symmetry between the v's and v's and taus. Right, this is just a generalization of the argument where on the previous slide this was the flux of v, but here it's a different variable, which is sort of, I can think of as a conjugate momentum to that flux. All right, so what this says is that really if I think of the Poincare, right, I could think of this problem, I could either impose boundary conditions on the v's or on the taus, which I could think of as either Dirichlet conditions or something like Neumann conditions. Right, and then I've got this Poincare-Steklov operator, which maps boundary conditions of v to the corresponding boundary conditions for tau. So the multisymplectic conservation law is really saying is that this sort of Poincare-Steklov operator is symmetric, right, on the boundary of any subdomain. Right, so this has sort of an interpretation as a reciprocity principle, like I had on the previous slide. Okay, so how do we write down a variational formulation for this that is sort of amenable to being tackled with the finite element method or a hybrid finite element method? So in fact, what I would really love to do, and this was our goal, is a lot of times if people want to construct structure-preserving methods, right, they know the geometric structure they want to preserve. Maybe they know the Lagrangian or Hamiltonian in advance, and they do something special. So if you know the Lagrangian, maybe you'll construct a variational integrator. But here I'd like to, if you think of structure-preserving integrators, if you know about that world, right, if someone hands you a system of ODEs, you can apply the midpoint method to it. Right? And if it just happens to be Hamiltonian, this is going to conserve the symplectic structure, but you don't need to know that in advance just to apply the midpoint method. You just apply the midpoint method. So what we'd like to do is actually to have a general class of methods where if someone just hands you a PDE in canonical form, you don't need to know whether it's Hamiltonian or not, but if it is, you would like the structure to automatically be preserved. All right, so suppose we've got a system of PDEs in this following canonical form, which a lot of PDEs are in, and I don't know whether these right-hand sides come from a Hamiltonian or not. I'm going to triangulate my domain into simplices k. And now let me multiply by arbitrary test functions v and tau that come from the same place as u and sigma, and integrate by parts. Right? And if I do that, I get this expression. I get something, I've got a sort of equation for the variations tau, an equation for the variations v. I've got something involving the boundary on the left-hand side, and the remaining thing involving the interior on the right-hand side. Right, so I've removed my derivatives on u and sigma by integrating by parts, and here my derivatives are of tau and v, the test functions. All right. Now, there are a number of ways to formulate what discontinuous Galerkin methods are, but one way that was done in this very nice unified analysis by Arnold, Bretzi, Coburn, and Marini about, I guess about 16, 17 years ago, was to basically do this formulation, but replace these boundary values of u and sigma by some approximate boundary values, which they call sort of a numerical trace and a numerical flux. And so this is right, more general than the kind of problems they were looking at. These are generally nonlinear. But the idea was usually that the boundary value of u, you might approximate that from, so if you've got two simplices that meet at an interface, right, u might have a particular trace on the left simplex and a different trace on the right simplex, so maybe you'll take the average of those or something like that. So it's usually something you compute locally in terms of the u's on the neighboring simplices, and likewise with sigma. A more recent development, just within the last 10 years by Coburn, Gopalakrishnan, and Lazarov, are what they call hybridizable discontinuous Galerkin methods. And the idea is that rather than defining this u hat and sigma hat as functions of things that are going on two different simplices, they actually take a hybrid approach and define them as new variables and satisfying some augmented variational principle. Right, so basically they take u hat to be a new unknown function on the boundary, right, and then the sigma hat is defined locally on each triangle, right, so it doesn't have to look at the neighboring triangle. It's defined entirely within a single triangle in terms of the u, the sigma, and this u hat, which is the new variable. Right. And in order to determine, right, we've got an extra unknown, so we need an extra equation, and the extra equation is this one, namely that this sigma hat has to basically at least weakly be single valued on interfaces between elements. So if this k comes up with its sigma hat and this k comes up with its sigma hat, then at least in a weak sense, right, those have to agree. Right, so this is again looking a little bit like the hybrid approach where I can think of u hat, right, which is this approximate trace of u. It acts like a Lagrange multiplier. And right, as with other hybrid methods, right, this gives a collection of local Galerkin problems coupled through these approximate boundaries. Right, and the nice thing about this approach is that depending on how you define the spaces that everything lives in and the sigma hats, you can recover a whole load of different types of methods. Right, so this is why they say unified hybridization of DG, mixed, and continuous Galerkin methods. Right, you can get some of the classical hybrid methods, classical mixed methods, the conventional just continuous Galerkin method with Lagrange finite elements, these various DG like interior penalty, LDG, you name it, all within this one big framework, depending on how you define these spaces and this function sigma hat. Okay, so finally, let me talk about what I mean for a method to be multisymplectic. I'm going to say that an HDG method is multisymplectic if, when I apply it to a Hamiltonian system, right, this integral vanishes. And this is basically saying that the multisymplectic conservation law holds, but right, instead of in terms of U and sigma themselves, in terms of the approximate traces of U and sigma. Right? So if this holds for every k, I say that it's multisymplectic, and I say it's strongly multisymplectic if this also holds for any collection of elements, right? Meaning that, right, not only is this conserved, right, per element, but also the conservation law sort of adds up properly in some sense. So I can take, right, well, not arbitrary subdomains as in the continuous setting, but I can take sort of arbitrary subdomains with the requirement that I'm not, taking fractions of a simplex. Right, so one of the theorems in our paper is that if a multisymplectic HDG method has what numerical analysts call a strongly conservative flux, meaning that the sigma hat is not only weakly single valued in the sense of orthogonal to a space of test functions, but actually is single valued. This is often used in the DG literature to mean the jump between, right, in these double valued things, then it's in fact strongly multisymplectic, right? So this condition is going to give you the fact that, right, if I add this up over several elements k, right, the contributions from any shared sort of internal facets is going to vanish. Right, so then this will imply that if we have a strongly multisymplectic flux. All right, so here is sort of the key lemma in our paper, which is that if an HDG method is applied to a Hamiltonian system, then we can re-express this integral over the boundary of the multisymplectic form in terms of something involving the jump between U hat and U and the jump between sigma hat and sigma. Right, and this is something that you can usually check directly from the way that sigma hat is defined. So we don't need to know anything about the numerical solutions. We just look at the definition of sigma hat and check whether this condition is satisfied. Right? And then sort of the main theorem is that, right, the following HDG methods are strongly multisymplectic. It's basically almost all of the ones in this paper of Coburn, Gopalakrishnan, and Lazarov. All right, so the Raviar-Thoma method written in hybrid form, Bretzi-Douglas-Marini, local DG. There's a hybrid version of a non-conforming method, the classic interior penalty DG method. In fact, the only one that's weakly multisymplectic but not strongly is the most classical one of all, which is just the continuous Galerkin method with Lagrange finite elements, which is kind of interesting. So it's weakly but not strongly multisymplectic, except in dimension 1. So when you're just doing, say, time integration. Right, so the takeaway of this is really that instead of using specially constructed finite difference or finite volume methods, if you've got a Hamiltonian PDE and you want to preserve multisymplectic structure, you'd pretty much be fine applying any of these finite element methods, sort of off the shelf. And this tells you that that structure is going to be preserved. The basic idea of the proof, just to mention one, so Raviar-Thoma and BDM, right, sigma hat is actually equal to sigma, meaning that this term vanishes, so this holds. The continuous Galerkin method and non-conforming take U hat equals U, and sigma hat's defined implicitly by that, right, so this term vanishes. Right, and the other ones, you need to be a little bit more clever, but not too much more clever. You just plug in the definition of sigma hat and verify that this is true. And here's, so the CGH method, the continuous Galerkin method, So here's an example with just two triangles where we assemble the matrix corresponding to the Dirichlet-Neumann operator, and as you can see, this is not a symmetric matrix. So in fact, you can actually come up with a very simple counterexample where that symmetry of the Dirichlet-Neumann map fails for the continuous Galerkin method, but all the others will satisfy this. Okay, so in the last 10 minutes or so, I'm going to completely switch gears. Well, not completely, because I'm still going to be talking about hybrid methods, and talk about a different problem, which is the problem of applying hybrid methods to gauge theory, right? And the issue of gauge symmetry and charge conservation, which is the conservation law that you get from Noether's theorem. So to motivate, let me talk a little bit about charge conservation in Maxwell's equations and how we would understand this from a variational point of view. So let's say that A is a time-dependent vector field on some domain in R3, which I call the vector potential. By the way, here I'm not going to be using a scalar potential. I'm taking what's called the temporal gauge, right, of setting that equal to 0. So you can get that from the space-time point of view, but I've skipped that step. All right, so I define the Lagrangian to be just 1/2 A dot norm squared minus 1/2 curl A norm squared, and here the norm is just the L2 norm on U. All right, if I do the Euler-Lagrange equations, one way of writing this in a way that's particularly finite element friendly is saying that for any variation A prime, right, I have that A prime A double dot plus curl A prime curl A is equal to 0, right, where this is the L2 inner product. By the way, I'm using primes for my variations rather than, the next letter in the alphabet, because B in electromagnetics means something very specific. So I'm just putting primes here to indicate variations. All right, so if I define the electric field E to be minus A dot and the magnetic field B to be curl A, right, what this equation says is that E dot is equal to curl B. And furthermore, if I just differentiate B equals curl A, I get B dot equals minus curl E. And if I take the divergence of B, well, div of curl vanishes, so divergence of B is 0. Right? So these are three of Maxwell's equations, but what happened to the fourth, which is the div E equals 0? By the way, here I'm talking about Maxwell's equations in vacuum without charge or current, but you can implement all of those things, just trying to simplify. So what happened to div E equals 0? Well, it turns out the Lagrangian is invariant under the following gauge transformation. So if I replace A by A plus grad xi, where xi is any scalar potential that is constant in time, all right, well then if I take the second derivative, right, the grad xi part vanishes because it's constant in time. Curl A is the same because curl of grad is 0. Right, so this is a symmetry, and the corresponding conservative momentum map is div E, right, which I can see from this, this weak formulation, right, just by taking my variation to correspond to an infinitesimal gauge transformation, right? So I just take my variation A prime to be equal to grad xi and plug it in here, right? And curl A prime then vanishes again because curl grad is 0, so I'm just left with the grad xi paired with A double dot is 0. So xi paired with div E dot is 0, and since xi is arbitrary, it can have arbitrarily small support. I have that locally div E is conserved. Right, and this means that, right, that if div E holds at the initial time, then it's going to hold for all time because, right, div E is a momentum map. And in fact, I could have any initial charge distribution at the beginning time, and this says that without any current, the charge distribution is stationary. All right, so I can incorporate all this extra fancy stuff from electromagnetics where we have D's and H's and J's and rhos, but again, I didn't want to go there in this talk. All right, so how do you do finite element discretization of Maxwell's equations? Well, again, we would start with this sort of weak or variational form of the problem. It turns out you have to be careful about what space you choose A from. If you were to use continuous piecewise polynomial vector fields for A, you'd actually get these incorrect solutions called spurious modes, basically this discrete curl-curl operator would have some, you'd get its spectrum completely wrong. You would, the eigenvalues would include some things that are not true eigenvalues. It will actually converge to the wrong thing. It's inconsistent. So in the 1980s, Nedelec introduced these two families called Nedelec elements of the first and second kind. And these elements are piecewise polynomial vector fields that have tangential continuity, but not normal continuity between elements. And it turns out that this, by two regular here, I mean, if you insist on continuity, you'll get your A to be H1 vector fields. In fact, you only want vector fields in a space called H curl, meaning that there's a weak curl, but not necessarily all the weak first derivatives. All right, so this perspective sort of later in the 80s and into the 90s by Bosovit and Katuga and some others related these to piecewise polynomial differential one forms where we can identify one forms in vector fields. And this was actually connected to some work by Whitney in the 1950s where he was interpolating sort of from cochains on a simplicial complex to the de Rham complex in order to prove de Rham's theorem. And this was later developed by various folks, including Arnold Falkenwinther, also Snorre Christiansen, Ralph Hiptmeyer, and others, into what's now called finite element exterior calculus, which is a way of doing differential forms, finite elements for problems involving differential forms. Right, so in that language, if I think of A and A prime as differential one forms on some domain, which is now no longer necessarily in R3, right? Instead of curl, I just write this as an exterior derivative. So I've got this problem. Right, and again, for this slightly more general problem, right, if I take A prime is equal to dc, I just have that d of d is equal to 0, right? The exterior derivative twice vanishes, so I get this kind of charge conservation law. All right, so in the last couple of minutes, let me just sketch out the picture for Yangmills theory. So if we have some Lie group G and a principal G bundle on our domain U, and if we have a local trivialization of this bundle, we can think of a principal connection as a Lie algebra valued one form. We can talk about the curvature of a connection locally in terms of a Lie algebra valued two form, which I write as FA, and that's dA plus 1/2 Lie bracket of A with itself. Right, and what this means is that I take the wedge product of the forms and the Lie bracket of these Lie algebra values. I can also define a covariant exterior derivative, which I write as d sub A. And if I differentiate twice, instead of dd equals 0, I get dA gives me the bracket of a form with the curvature 2 form. Right, so that takes it up by 2 degrees. All right, so this is my generalization of the Lagrangian, and this gives the following Euler-Lagrange equations. This second part, right, instead of the curl-curl operator, I get the Yang-Mills operator, right? And if I look at the stationary solutions, I'm just talking about the Yang-Mills equations, and you can think of this as a sort of a second-order flow related to the Yang-Mills equations. Right, and Maxwell's equations are just the case where my principal bundle is a trivial U1 bundle, right? Because the Lie algebra of U1 is just the reals, so I just have ordinary real valued one forms, which I can imagine, or which I can think of as vector fields. Right. Here, if I take A prime as the covariant exterior derivative of a scalar potential or a 0 form, sorry, not scalar potential, I guess it's a G-valued 0 form, I get this conservation law, which is sort of a version of charge conservation for Yang-Mills. And let me just briefly say what the problem is with the previous approach. Why can't you just naively do what we did for Maxwell's equations and use these finite element differential forms? Well, the reason is that it has to do with this Lie bracket term, right? So if I've got an abelian Lie group like U1, then the Lie algebra bracket is trivial. But if I'm on a non-abelian group and the bracket is non-trivial, suppose that my A's have degree R, and I pick a Xi of degree greater than 0. Right? Then that means that the degree of the bracket of A with Xi has degree too high to be in my finite element space. Right, so this thing I need to do for my symmetry, taking A prime as dA of xi, right, this is no longer a valid choice of A prime. Right, so basically what my symmetry, what is normally a symmetry transformation for the exact system, sort of increases the degrees of my polynomials, and therefore it's not a symmetry at all. It takes me outside the space that I'm looking for solutions and variations in. Right, so this was observed by Snorre Christensen and Ragnar Winther in a 2006 paper, and they addressed this by, I guess, doing what they tell you never to do in geometric integration, which is say, okay, well, this momentum isn't conserved, so at every step we just project onto the constant, momentum constraint. Sort of like using Euler's method and then projecting onto linear and angular momentum, which is really not ideal. And an observation is that, well, in fact, we could do this if xi were degree 0, because that would be a valid variation. But the problem is, if we're using continuous finite elements, right, if I've got a degree, like a degree 0 polynomial, this has to be not just locally constant, but globally constant, right? Which means I no longer get a local conservation law if I take xi to be constant. I just get global conservation of charge, which is something fairly trivial. So our idea was to use a hybrid approach that allows us to take xi to be piecewise constant, and that does in fact give us a local conservation law. So just, and this is my last slide. Our idea is we introduce, to take a hybrid approach, introduce this new Lagrange multiplier H hat, and this really is like the magnetic field H that you'll see in Maxwell's equations, sort of an approximate trace to it. We relax continuity on A, and we add this sort of penalty term to the Lagrangian. We end up with these as our Euler-Lagrange equations. So instead of 0 on the right-hand side, you get this integral over the boundary involving h bar, along with continuity coming out from the Lagrange multiplier and forcing it. And this is true, this is not true on the entire domain. This is for each k, this first one. So this first one is entirely local. We can then define a trace version of, so this is sort of one of Maxwell's equations without current. D dot equals curl H. Here D is dual to E and H is dual to B. Right, and we can do the following to actually recover what D hat is. Right, and so if we take our xi to be just 1 on a single element and 0 everywhere else, because now we can take discontinuous piecewise constants, we in fact get that this basically trace version of charge conservation holds for every single element. Right, and this idea extends to arbitrary gauge groups, right, abelian or non-abelian, and we can also do non-trivial bundles by basically having gauge transformations that sort of do a little something saying how the interior of each element is sort of glued to its boundary into the neighboring elements. So the conclusion, is that in the language of classical finite elements, it's difficult to express local symmetries and conservation laws, which is why a lot of work is focused on finite difference and finite volume methods. Hybrid methods give us a very natural way to talk about this. We can look at conservation laws that are satisfied by these approximate traces that show up when we hybridize. For Hamiltonian PDEs, it turns out a whole lot of methods are multisymplectic structure preserving. And for Yangmills theory, the advantage of this hybrid approach is it allows us to take piecewise constant gauge transformations, which are actually local symmetries of the method, whereas the continuous finite element formulation does not have any local gauge symmetry. And consequently, we get per element charge conservation laws. Okay, well, thank you very much.
So we have time for a few quick questions. This is being recorded, so you can speak into the microphone.
Okay, very brief one. For the gauge theory story, do you need to know the gauge group explicitly, or do you, like, what are the conditions?
What do you mean? Do I need to know the gauge group explicitly? Well, so the gauge group and the principal bundle and all that are part of the specification of the problem.
But the typical thing, you have a Lagrangian, but you don't know all the symmetries. Then are you like good still or not?
I mean, I'm not completely sure I understand the question. I think for this problem, in order to even specify the problem, I would need to say what bundle I'm working in, right? And if I know the bundle and I have the, and I know the Yangmills Lagrangian, then I know what my gauge transformations are. So in this case, I do know in advance what these symmetries are. So this is maybe a bit of a contrast to the first part of the talk. Here, I'm not talking about a general technique. This is a very specific class of equations. Yeah.
I have a question related to the incompressible Euler equation for invisible fluid flow.
Okay.
Did you try that, or I mean, what wasn't really clear to me is that I mean, do you always need a Hamiltonian structure or not? Maybe not.
So the question is, do we always need Hamiltonian structure? And the question was about inviscid Euler's equations for inviscid fluid flow. So no, I haven't looked at applying this first class of methods to. So the short answer is no. I have not looked at applying these to fluids.
Okay, so let's thank the speaker one more time.